Good morning, everybody. In the notes or the chat room, please be reminded that our first midterm would be on July 1st. There will be another one, the second midterm on July 18, and the final, according to the campus, should be on August 4th. So we have 3 exams, each one of them will qualify for 20% of the grade. Your assignments qualify for 40% of the grade. What we'd like to do today is cover another topic related to the weak force or radioactivity. And that is the fact that radioactivity under our feet generates heat in the Earth crust and has 2 major effects. One of them is that it contributes to the generation of the Earth's magnetic field that protects us from excess radiation from our star, the sun. And it's interesting to realize that we owe life on Earth for 2 effects: a nuclear effect from radiation from our star, the sun, and radioactivity under our feet provides the magnetic field that protects us, causes the dynamo, the Earth's dynamo, and the Earth's magnetic field. It has interesting implications on nuclear installations, is that the Earth's magnetic fields protects us against events that can happen on the sun, like ejections of plasmas toward the Earth. And another interesting aspect is the fact that radiation in the Earth's crust provides us with another form of energy considered as renewable, which is the geothermal energy. So this is the topic that I'd like to cover today. So we go and share the screen here and let us make it simple here. We go to the Nuclear Power Engineering web site, and we'll find that the terrestrial radioactivity in our Earth's crust could be the basis of a form of energy that we call geothermal energy. And at the same time, it is the cause of the Earth's dynamo, the generation of the Earth's magnetic field. So we consider the Earth as a radioactive heat engine. And in fact, it is interesting to know that the Earth is a power generator from the perspective of radioactivity. Knowledge about it comes in from different experiments. For instance, this is the liquid scintillator detector in Japan, and it is detecting anti-neutrinos that come in from the sun and other parts of the universe, in fact, hitting the Earth. And it can go through the whole Earth without really interactions. But if you look at the composition of the different elements in the solar system, you'll find that obviously the most common element is hydrogen, as you could see here, in terms of the abundance relative to silicon, which is considered as 10 to the 6 or 1 million. You'll find that helium would be 10 to the 6. If you go to 1 million here, that is silicon. Oxygen, carbon, and neon, interestingly enough, are also much more abundant than silicon. Iron is as abundant as silicon, but we have some of the heavy elements now that are much, much less abundant than silicon, 1 million times less in abundant. And these are the heavy elements like lead, platinum, mercury, and so on. The Earth is thought to have been formed in a cataclysmic event that happened 4.6 billion years ago. If we consider the age of the universe, or the farthest light that we can detect as at 13.7 billion years away from us. So in a way, the formation of the Earth is young halfway through the age of the universe, and hence the discussions and the speculation about the Fermi paradox that cosmologists are engaged in that case. We measure the distances in our universe with the distance between us and the sun, and that is called 1 astronomical unit. The important aspect of the work today is that the Earth is in fact a radioactive heat engine. Those elements that were formed in that supernova that formed the Earth, then of course the remnants of the supernova were grabbed by gravitationally by our star, the sun, including the other solid rocky planets, if you want to call them, like Mars and Venus. The other outer planets are primarily hydrogen planets, like Jupiter is hydrogen with such a high gravitational field that at the center of it, hydrogen is so highly compressed, it acts like a metal. And in fact, if you look in the periodic table of the elements, the first column containing hydrogen is a column containing metals. In the formation of the supernova, heavy elements were formed, including uranium and thorium, but other elements were also formed as far as we know, like the isotope aluminum-26. That one had a short half-life, 7.3 10 to the 5th years, and it has disappeared. It's not there anymore. However, potassium-40 has a half-life of 1.2 billion years, so it is still existing. And it is part of our body. It forms a part of the electrolytes that allow our muscle systems and our organs to function. And if you look at a bottle of Gatorade, you'll find that it is included as part of the components of the liquid that athletes use or other people as Gatorade. The origin of it is that one of the sports team in Florida, the Gators, discovered that their athletes being trained in the summer lose lots of sweating, and in that case they lose electrolytes from their body. So they invented a drink to substitute those electrolytes, the potassium, one of them, sodium, of course, chloride, salt, and then they commercialize it as Gatorade. So check it out. The 0.01% of potassium is the potassium-40. So whenever you drink Gatorade, you get some potassium into your body as an electrolyte. But it is also common in other foods, like bananas contain significant amount of potassium-40. There is nothing to fear about it. It's part of nature, and we cannot get rid of it. And it exists in the Earth crust, and it is radioactive as much as uranium and thorium. Other elements are listed here: tellurium, neodymium, samarium. All these isotopes have different half-lives, some of them shorter than the others, like palladium 107, 6.5 million years. But look at cerium-142, one of the rare earth elements. It's larger than 10 to the 16. We don't know exactly how much. People have struggled to determine what is the half-life in that case. And we come also, of course, to our thorium-232, 4 times more abundant than the Earth crust, than uranium-238 and uranium-235 and uranium-234. All right, so all these radioactive elements exists in the Earth crust, less so in other planets like Mars. Mars is a solid rocky planet, but does not contain as much radioactive elements as the Earth. Hence, it has a very local magnetic field, and it doesn't have the same protection from the solar wind as the Earth has. So its atmosphere has been depleted by the solar wind. So the atmosphere on Mars is very, very, very thin. And a future base on Mars would have to find ways of shielding the astronaut there to the same extent, say, as our atmosphere shields us against the solar wind, as well as the Earth's magnetic field. All right, so if the Earth contains all those interesting radioactive elements, so what is the energy release in that case? We can calculate it, in fact, by taking the activity of those isotopes for each one of those isotopes, A sub I. We take the magnitude of the activity, which is a decay constant of the isotope, by its abundance or number of nuclei as a function of time. The units here would be becquerels or transformations per second. And that Ni of T, we know according to the law of radioactive decay, is Ni sub 0 e to the minus lambda T. We can turn this activity into power by multiplying the activity of each one of those isotopes listed in the table by the energy, or the most important average energy of each emission of radioactivity. So in that case, you multiply that activity here by E sub I, the energy release per disintegration, and you get the power released in million electron volt per second, because here we had transformations or decay per second. You multiply by energy, million electron volt per transformation, it becomes million electron volt per second. Energy per unit time is power. So in fact, this is the power generated by each isotope in the Earth's crust. If you go and sum all of them over all the isotopes here, you can get the total power generated in the Earth's crust. And you'll find that the total energy release now would be the integral over time P of T dt from the time where the Earth was created up till now. And you notice that a huge amount of energy has been produced over the lifetime of the Earth. We can use Avogadro's number here to determine what is the initial number of the isotopes of interest. And in that case, because we know really the distribution in the previous graphs that I've shown earlier, showing the different distribution of different elements in the universe are different on Earth, and interesting enough, the composition of the moon is similar to the composition of the Earth, suggesting that the moon has been formed by another cataclysmic event, a collision between two solar bodies, maybe between Mars and the Earth, a long time ago, and the moon and the Earth have similar compositions as far as we know. So if we use Avogadro's law there with the masses of the different isotopes, we can get basically a total expression for the total energy over time that has been generated by the radioisotopes in the Earth's crust. And the estimate that we know of the power is that we have 25,000 gigajoule per second, or gigawatts, being generated by the radioactivity in the Earth's crust. If you consider that a typical nuclear power plant has a power of 1,000 gigawatt, a megawatt, one gigawatt is 1,000 megawatts, then that is the equivalent of 25,000 nuclear power plants of power generated inside the Earth. The important aspect of this is that the affects the composition of the Earth. To the best of our knowledge, the Earth has a solid inner core surrounded by a liquid outer core. That liquid comes in, of course, as far as we know, from that process of radioactivity, followed by a mantle and the crust. And the interesting aspect of it is that as humans and all life on Earth basically lives here on the crust. Now, the solid inner core and the liquid outer core are composed of heavy elements. The most abundant elements on Earth are iron and nickel. So it is thought that the solid inner core and the outer core are composed of nickel, and then some oxides now form the mantle, followed by the crust. And the crust, of course, contains all our oceans. 70% of the Earth's surface is oceans. Now, the fascinating thing is that the Earth rotates around its axis with at an angle of about 23.5 degrees. Now here you have a liquid metal, iron and nickel, that contain lots of electrons rotating around the Earth axial magnetic field of the Earth. And this is the formula for a dynamo or an electrical generator. So in that case, as the Earth rotates, that liquid is rotating like a dynamo, generating a magnetic field. Notice that the earthquakes and volcanoes really occur at the very, very, very top of the crust of the surface. It's identified that the upper mantle, the lower mantle is basically metal oxides. The liquid outer core is an iron alloy, and the core in the center is solid metal and nickel. So the rotation itself, that's a simulation on a supercomputer, generates a magnetic field because now in that case, the right-hand rules of electromagnetism tells me that if you have a current in the direction of your fingers in your hand, you find yourself generating a magnetic field in the direction of your thumb. So the rotation of the outer core layer generates a large magnetic field. And of course, the North Pole would be at the north here, the South Pole would be at the south. In fact, if you, a trivia here, idea here is that when you use a compass and you say, oh, the needle is pointing to the north, well, it's opposite poles that attract each other. So in fact, the North Pole on your compass is pointing to the South Pole of the Earth. So the designation should be south and north, but people still call it north and south in general. So the Earth's magnetic field in space generates a magnetic field that goes to very large distances away from the Earth. Now, the Earth is subject to the solar wind that is impinging on the Earth. And the solar wind is composed of electrons and charged particles, protons, and it would be hitting the surface of the Earth like it has been hitting the surface of Mars. And if it hits the surface of the Earth, it would simply evaporate its atmosphere or evaporate its oceans out into space. And water is where life has flourished, and that's how life has in fact started here on Earth. So the magnetic field of the Earth acts as a shield against the solar wind hitting the surface of the Earth. In fact, it composes two areas, toroidal areas around the field here. These are called the Van Allen belts. And the Van Allen belts are very important in communications and spaceships. You would not obviously place astronauts in the area where those charged particles and very high levels of radiation exist. Communication satellites are, for instance, those in geosynchronous orbit are placed outside the Van Allen radiation belts. Some astronauts, interesting enough, didn't know that they are being sent into space through the Earth, the two Van Allen belts. In that case, they can be subject to radiation in general. The interesting thing then is that the charged particles from the solar wind are trapped into the Earth's magnetic field, and some of them, as you know, charged particles rotate around the magnetic field lines. So if they are trapped around the magnetic field line like this one, they rotate from the North Pole to the South Pole. They get squeezed at the bottom here and at the top. Some of them find their way down to the Earth and generate the aurora borealis, or the northern lights. And then the South Pole, they form a big circle, and that is the aurora australis, or the southern lights. Most of the other particles that are not trapped into the Van Allen radiation belts are simply thrown out into space. So the Earth is surrounded by a radiation belts, and it's also radiation by what's called the plasma sphere. Plasma is a state of matter where the electrons and the nuclei are separated, so they are ionized in case. And it's very important, of course, that sometimes those radiation belts expand if there are solar flares, and you'll have to, the electrical engineers have to think about hardening any communication satellites or GPS satellites or out in space. They are positioned, as I suggested here, away out of the radiation belt for two reasons. First, radiation would destroy all the solid state components, and they have to be hardened against the radiation itself. So too much of the solar wind would strip the Earth from its water, its atmosphere, and we would be a dead planet like Mars. Mars, in fact, has a local magnetic field because it doesn't have as much radioactive materials as the Earth to generate that dynamo effect that protects our Earth against the solar wind in general. However, as we said, that heat is generated from those radioisotopes in the mantle of the Earth, the upper mantle and the crust. And they observed in the mining industry is that when they dig deep, for instance, in South Africa, mining gold, that every 100 meters that they dig into the mine, the temperature increases by 3 degrees Celsius. And calculations were done, and we suggest that they suggest that the crust insulates the core and leaks very slow heat at a rate of 0.06 joule per second per meter square. So if you consider the total leakage on the Earth, that's 8 × 10⁻20th power joules per year. And look at this. This is minor in comparison to the heat incident on the Earth from the sun, which is 170 million gigawatts. So these are orders of magnitudes of heat flows in the Earth. Terrestrial energy generates 3.2 × 10⁻13 watts of energy. Convection in volcanoes and hot spring, 3 × 10⁻11 watts. Tidal energy, which is energy generated from the attraction between the moon and the Earth, is 1 order of magnitude lower. In fact, tidal energy is if it can be exploited, depending on the geography of the shores of the continents, is also another form of renewable energy. And in that case, that energy generated in the Earth crust is exploitable in what we call geothermal energy, and we identify that it is caused by radioactivity in the Earth's crust. We can compare this to solar radiation. It's very minimal compared to solar radiation. The instant radiation from the sun is 10⁻17 watts in power. Some of it is reflected back to space. Some is converted to heat. This is heat that is available in the atmosphere of the Earth. Of course, solar radiation absorbed from the sun is converted into winds and waves, convection and currents in the ocean. Since we have wind energy as well as we have solar energy from the direct incident radiation. So you could see here that we have power flows from different sources in the Earth's crust. And the crust of the Earth is nothing than plates that are floating on top of the mantle. 8 plates are identified: the Eurasian plate, the Antarctic plate, the Eurasian plate. And when they rub against each other, oh, we get earthquakes. But they also sometimes allow the magma or the molten rock to escape to the surface of the Earth. When the plates interact with each other, you'll find that the magma can leak out of the Earth's surface, and we get volcanic areas. So this is a description of the Earth's tectonic plate. And as the Earth is for instance, look here, the Pacific plate has volcanoes all the way surrounding it. Like if you go to Japan, for instance, if you go on the west coast of the United States, the west coast of South America, in the Atlantic, we have two plates that are subducting one into the other. In fact, if you look at the geometry here, you could see that the African plate and the American plate at some point were joined together right here. In that case, they are separating, and that provides us with the deepest parts of the Atlantic Ocean. Because those plates rub against each other, you'll find that heat is generated and rock is molten, and all of these are volcanoes surrounding the Earth's tectonic plates. And in that case, it can be used. In fact, it is being used in many parts of the world, even in the Mediterranean here in Italy, for producing power, because all you have to do is, if the magma is close to the surface of the Earth, you can inject fresh water, turn it into steam, and the steam can turn turbines and produce power for us. So this is these are the seismically active areas along the tectonic plates of the Earth. Of interest, and that's another chapter that you can read yourself. And along those tectonic plates, you'll find also the regions like in Indonesia, Malaysia, where hydrocarbon deposits are close to the surface, like oil deposits. So some people suggest that maybe the Earth produces its own hydrocarbons, like in some moons in the solar system. And in that case, this hydrocarbon, if it is being produced, could be also an infinite source of energy, and that we are depending today only on the sedimentary forms of hydrocarbons, oil, and coal, but not coal, obviously, in that case. All right, so how this geothermal energy is being produced by the different plates moving against each other. In some regions, they basically, you get a subduction zone. One of the plates goes below the other plates, they rub against each other, the rubbing generates heat, and basically you get molten rock, and that molten rock is close to the surface so that we can access it to generate steam. So a geothermal plant using geothermal heat is a simple design. In that case, you locate an area where the magma or the molten rock from the Earth is close to the surface. And this means that you really have to visit once in your lifetime our Yellowstone Park, which is a volcano. In fact, the caldera or the cauldron of a volcano very close to the Earth. You find that the water from rain is so close to the magma or the molten rock below the surface, miles below the surface, that you get the events of the geysers, and it's something to visit once in a lifetime. However, it is also used for the production of power, and we are interested in the production of power. Now that power is produced from, guess what, radioactivity in the Earth's crust. So what you do is that you inject water, say, that's available from a lake, maybe fresh water, into a geothermal reservoir, rocky formation above the magma. The water there evaporates from the heat from the Earth, the radioactivity in the Earth. You get a production well where you extract the steam now, put it through a turbine, and produce power. And this is happening in many different parts of the world. Natural sources of steam are available, except that maybe for Yellowstone, the Yellowstone Park in the United States, it's the site of a vast super volcano. If it erupts, it can affect the United States in a very negative way. And this is left as a nature preserve. And this is a natural geyser. So if you find your way to the Yellowstone Park, you could see those geysers, steam coming out of the earth, hot water, very acidic, to the point that they fear that some people who fell into it basically were dissolved, literally dissolved. But it shows us really that the earth is a very, very dynamic system. You can, it's not just displayed in the form of the geysers, but you can get what's called the fumaroles. So that is parts in a muddy spot maybe where sulfur dioxide, primarily mixed with steam, is emitted out of the ground. So there is heat there under our feet. And it has been exploited in New Zealand to a large degree. You could see here that one of those geyser fields, instead of having it as a natural kind of a park like in the United States, they installed all that piping here, and they're using the steam to run turbines and produce electricity. Something very interesting about Iceland. In Iceland, most of the power, really, 90%, 99% of it is being produced from their geothermal plants. This is another area that's where the heat, geothermal heat, heat from radioactivity in the Earth's crust is exploited on a large scale. As you could see here, that is in Italy. So even in the Mediterranean area in Tuscany is has a use of that geothermal energy. Iceland, as I suggested, its total power generation is from geothermal energy. So that's radioactivity, in fact, and we have to be aware of it in general. Some people have thought about producing artificial geothermal fields. And in that case, peaceful nuclear explosions have been suggested. So you would explode a nuclear device underground. You would produce a cavity first. The cavity collapses, produces a large cylinder of rock that is close to maybe a magma area. You inject water, cold water into it. You can generate steam and you can rotate a turbine. This has been suggested as one of the peaceful applications of nuclear explosions. You create basically a fractured zone to extract the heat from water that you inject into the zone. The idea has been modified into what we call today fracking or hydraulic fracturing. It's not nuclear devices now used to fracture the medium as initially suggested. There is no reason why it cannot be used in the future, but at least the idea of fracturing uses chemical explosives to fracture the medium and then inject sand under high pressure into it and extract gases, natural gas, methane, CH4, or liquid, even hydrocarbon, petroleum from tight formations. And that is very common in the United States today and increased our supply of hydrocarbons in general. If we mention this, we have to mention the Yellowstone super volcano. In fact, I spent 2 weeks this summer visiting it in between the last semester and this semester. People are worried that it could become active again, but its eruption happens every 60,000 to 100,000 years. We shouldn't worry about it. But NASA has suggested that we might like to decrease the heat generation in a large magma bubble under the park to prevent it from erupting. And so studies are being made about extracting some of the energy that is present in the Yellowstone supervolcano. If it erupts, it can cause great damage in the United States and even the rest of the world. As I suggested, some people suggested also that because you notice like areas like Indonesia, the west coast of the United States, where volcanic activity is high, you'll find that hydrocarbons occur. So the suggestion is that maybe the Earth is creating its own hydrocarbons, and it becomes a topic or a discussion between Ukrainian and Russian scientists who suggest that the Earth creates its own hydrocarbons. So they go and drill just about anywhere, and somehow they do find oil fields. And the Western scientists who suggest that oil fields are caused by sedimentary formations where living matter like plankton in the oceans have decayed into the hydrocarbon. So in that case, you'll find that the United States have a great geothermal potential in the western part of the country, in the Rocky Mountain and the western states here. So this is an area where geothermal heat can be exploited, not so on the, or to a lesser degree, on the East Coast. And it shows you the different temperatures of the heat generation in the Earth's crust. Notice here, this is a huge potential in the Rocky Mountain and the Sierra Nevada. Parts of the world where geothermal heat follows some kind of a pattern, like here around the Pacific, that's there is a big ring. It's described as the ring of fire. So that geothermal heat follows it where the tectonic plates of the Earth are meeting each other. Here is in the Middle East, around the Red Sea and the northern part of the Mediterranean Sea. And you hear about Pompeii and the eruptions of volcanoes in the Mediterranean area. If the contribution of radiogenic and the formational energies are separated, one should be able to deduce the Earth's surface temperature at times past. If you combine the sources from uranium-238 and thorium-232, that is about 20 terawatt today. Thorium is 4 times more abundant than uranium in the Earth's crust. And basically, you'll find that the half-life of uranium is 4.47 billion years. So its power source would have been 8.94 terawatt in the past. The formational energy is decreasing because radioactivity decreases at the rate of 21 terawatt today. You'll find that you can deduce when the crust formed and when the biological life would have started on Earth. So this is about how radioactivity contributes to geothermal energy formation. If you are interested in the topic of whether petroleum has an origin that is sedimentary or whether the Earth is producing its own petroleum, hence, well, we have, in that case, an unlimited supply of petroleum. Please go and read the chapter on biogenic and abiogenic petroleum. I'll leave it for your own interest. I'll allow for questions here in the chat room before I go to the next chapter. We have no questions, so I'll go now to our next chapter. And in that case, we are going to start on the study of nuclear reactors, fission systems, and thermodynamic cycles. And what I would like to do today is study first the fission reactors, and then we'll give some time later in the semester to study fusion possible reactors for our futures. However, we know, of course, that most nuclear power plants use the principles of thermodynamics to produce power. In that case, we use a steam cycle. But in terms of the conversion of different forms of energy, we'd like to supplement the laws of thermodynamics that always, of course, apply to all those situations into, oh, I have to share the screen here. I have to be careful to go back and share the screen. Let me see here. I should have been told that I should start the video and share the screen. Go back here. So we're starting on the chapter on nuclear reactor concepts and thermodynamic cycles. What we'd like to do here is study how today we are extracting energy from fission reactors, but also look at the designs that are under considerations, like the generation 4 reactors, and some concept that could be thought about for future different applications. So now in that case, we consider fission systems in general. The laws of thermodynamics, as I said, do apply, but there are some other underlying principles that apply to energy conversion from one form of energy to another. In that context, we have to realize that energy is extremely abundant in the Earth and the universe in general. And in fact, for us to, according to the Kardashian ideas, and to reach a level 1 civilization, we cannot continue depending on our fossil fuel supplies of dead animals and dead plants, because they're depletable. They won't be there in the future. And to reach a level 1 civilization, guess what? We have to depend on nuclear energy, particularly the energy available on our own Earth, before even thinking about fusion, which would be energy from our star, the sun in general. So what we'd like to do is look at some principles of energy conversion from one form to another. And you'll see that if we master those principles, then we can innovate and invent new ways of extracting all forms of energy from the environment and serve society according to what society needs from us, engineers and scientists. Whatever form of energy is needed, we will provide it to the well-being of society in general. So there are some principles that are not enunciated in the other textbooks, if you consider that a web textbook, that they do not supersede the laws of thermodynamics, but they apply to the narrower branch of energy conversion from one form to another. So let's state them very simply and try to understand them so that we can innovate and produce new ideas in terms of energy production. The first principle or observation is the following, is that energy can only be extracted from a flow system. We cannot extract energy from a system that is stagnant, that is not moving. So if we want to extract energy from the environment, it is very obvious that we have to have a system where energy flows from a high energy reservoir to a low energy sink. So that's a corollary. That is a corollary to the first principle of energy can be extracted from a flow system, and only a flow system. And in that case, we need to have a high energy reservoir and a low energy sink. Let's take example for this. If you think about a hydroelectric plant, you have a lake where water is stored. And in that case, that water is stored contains or possesses potential energy. You can calculate this as mgh, the mass of the water multiplied by the gravity acceleration, g, and h, say the height of the water in the reservoir. If you do not allow the water to flow through the turbines in the hydroelectric plant, that energy is stored there a while, fine, behind the dam, but it is not producing, you cannot extract energy from it. So if you want to convert your potential energy into kinetic energy, the rotation of the blades of the hydraulic turbines, and then turn it into electricity, you need to allow the water to flow. And it could be a waterfall, a natural waterfall, like the Niagara Falls, or the ingenuity of humans is that we build also dams, like the Hoover Dam in general. Because you have to generate a flow system, some energy stored has to be allocated to the flow itself. And only part of that energy then can be extracted by the hydraulic turbine. In a heat engine, like you have studied in your thermal classes, the heat energy cannot be extracted from a totally insulated reservoir. Let's take the gasoline in the tank of your car. You cannot extract it if it's sitting there in the tank. You have to get it to flow into the engine, and you have to move it from a high temperature reservoir where the fuel is ignited to the environment and release the heat to the environment through a radiator. And since we're talking a minute ago about geothermal energy, you have to use a differential temperature deep underground close to the magma and the Earth's surface and allow for some energy flow. You inject water, cold water into the close to the magma, and then you get steam out of it. In ocean thermal energy production or in solar ponds, as a matter of fact, you take to advantage the flow of a medium like ammonia. You evaporate it near the surface in the solar pond or at the ocean surface, and then let it condense in the cooler bottom of the ocean. In that case, you use a low boiling point working substance such as ammonia on the surface and get it condensed at the cooler depths in the ocean bottom. Another interesting application, since we are not just talking about thermodynamic cycles, we are also talking about aerodynamic cycles. Let's take wind power generation. You notice that wind turbines have maybe preferentially 3 or 4 or 5 or 10 blades turning in the wind. If you get a totally flat surface and try to block totally the wind and have no rotation of the blades, you cannot extract energy from the wind. What you do there is simply slow down the speed of the wind from upwind from the wind turbine to downwind from the wind turbine and let the wind flow. If you do not allow the wind to flow, you cannot extract energy from the wind. So in that case, you have a flow system from a region of high speed of the wind upfront or upwind to a region of low pressure, lower pressure, or behind the rotor blades, and a flow system is established. So a flow system is needed for the conversion of one form of energy to another, not just thermodynamic energy, but as I suggested, potential energy, hydroelectric power, OTEC power, wind power. So it's much more general than just thermodynamic principles. A second principle can be stated as only asymmetries in a hydraulic, kinetic, thermodynamic, or aerodynamic system allow the extraction of a portion of the available energy in the system. So we need, in that case, an asymmetry. In the Niagara Falls, for instance, you have water with a high potential energy, and when it falls down through the falls, it has now a lower potential energy. So there is an asymmetry there. In the wind turbine, there is an asymmetry in the speed of the wind ahead of the upwind from the turbine and behind the turbine. I'm taking examples here that are not necessarily thermodynamic in general. And taking that into consideration, this asymmetry can occur in nature, like the Niagara Falls has an asymmetry in the potential energy of the water up the falls and a lower potential energy at the bottom of the fall. But because we can create that situation if it doesn't exist in nature and exploit it, we develop ingenious devices as engineers and scientists, and understanding that if you just create an asymmetry, you can extract energy from the environment. So this suggests that ingenious people, conceptualized by ingenious people, take advantage of naturally existing asymmetry. Alternatively, ingenious artificial configurations or situation favoring the creation of these asymmetries are created to extract energy from the environment. Wind turbines are an example. Hydroelectric plants are another example. A third principle that we can list for energy conversion is that the existence of a flow system necessitates that only a fraction of the available energy can be extracted and at an efficiency characteristic of the energy product extraction process, with the rest returned back to the environment. So this is now a different definition of efficiency, the thermodynamic efficiency of the Carnot cycle efficiency that states that the efficiency is equal to the temperature differential, the Carnot cycle efficiency, delta T divided into the energy extracted divided into the energy that is available to us. So in that case, the definition of the efficiency here is that because you need a flow system, I repeat here, because you need a flow system, that flow system has to attract some part of the energy that is available to you. Hence, you have an efficiency associated with any one of these energy conversion processes. So the corollary to that third principle of energy conversion is that the conversion efficiency is proportional to the width of the existing natural or the created artificial asymmetry. So if the in thermodynamics, of course, or heat systems, the ideal heat cycle efficiency is expressed by the Carnot cycle efficiency. However, we are also extracting energy from aerodynamic system, the wind stream. The ideal aerodynamic cycle efficiency is expressed by Betz efficiency equation. So it's you'll find that for each form of energy extraction, there is an efficiency extracted for it, which is the maximum amount that you can extract, or an ideal amount that a heat engine or an energy conversion process, whether it's a heat engine or a wind turbine, an aerodynamic system, or a hydraulic turbine in a hydroelectric plant, can extract energy. And the definition there is has to be expressed by really how much energy we have to allocate to that flow idea concept that I explained at the top. If we master those principles here, we open ourselves a window to develop new ideas. For instance, if an asymmetry does not exist, we create the asymmetry. Once we create the asymmetry, then we can extract energy from the environment. Going back to nuclear power plants, of course, use the same energy conversion principles, and there are as many designs of nuclear power plants as you have designers. All you have to do in that case is create a compatible system of a coolant, a fuel, a moderator, a control system, and create the asymmetry in that case, and you can extract energy from the environment. So the laws of thermodynamics apply to all energy conversion systems. It's that energy conversion itself has some principles of operation requiring a flow system and asymmetries in the process. So if we go back to the laws of thermodynamics, the first law is the law of conservation of energy. It tells us that energy cannot be created or destroyed in an isolated system. The change in a system's internal energy is equal to the difference between the heat added to the system from its surroundings and work done by the system on its surrounding. So the first law basically addresses the interconvertibility of work and heat as forms of energy. So the internal energy is defined as the heat plus the work, and we designate it symbolically as du is equal, or the change in the internal energy is equal to dq, the heat added or extracted from the system plus the work done by the system. A different perspective is that matter and energy, in that case matter and energy, are equivalent. It cannot be created nor can it be destroyed. The quantity of matter energy remains the same. It can change from solid to liquid to gas, plasma, and back again. But the total amount of matter and energy in the universe, according to the first law, remains as a constant. The second law of thermodynamics suggests that all spontaneous processes produce an increase in the entropy of the universe. And we This is a principle of irreversibility, and we define in that case the entropy as the change in the heat energy in a reversible system divided into T. And T here, when we deal with thermodynamic, is not the Celsius temperature, it is not the Fahrenheit temperature, it is the Kelvin temperature. So we have to be aware of this, and that suggests basically that for an irreversible system, ds, or the change in entropy, is larger than dq over T. The third law of thermodynamics suggests that the entropy of a system approaches a constant value as the temperature approaches 0. And I'll leave this to your classes of thermodynamics to deal with them. But we go back to nuclear power plants, the fission systems, or fusion, in fact, that also would apply, is that we try to define differences between different systems according to their power density. And power density in that case is defined as the energy produced by in unit volume of the material. So in that case, if you take the power in megawatt, thermal, meaning that thermal energy, not electric energy, and we know that electrical energy is equal to the thermal energy multiplied into the efficiency of the conversion process. So the specific energy, the volumetric energy, or uses units of megawatt thermal per cubic meter. And in that case, we are going to figure it out later on. It's a product of the flux. This is the average neutron flux in neutrons per centimeter squared per second, multiplied by what we are going to call the macroscopic fission cross-section, multiplied by into E sub F, which is the energy release per fission event. In some textbooks, it's 200 million electron volt per fission. In earlier chapters, because of we cannot extract the energy of the anti-neutrinos, and we suggested it should be really 180 million electron volt per energy, per fission event. Along these lines, you'll find that we have designs of nuclear power plants that have different power density, different values of that Q parameter. And you'll find that it varies from, say, 75 megawatt thermal per cubic meter, all the way to 530 megawatt thermal per cubic meter. The lowest level of average core power density is what we call the high temperature gas-cooled reactor. So from the definition itself, the acronym is HTGR. This is a system that operates at high temperature, is gas-cooled, and moderated by graphite, very much like the Chicago Pile #1 that was moderated by graphite, but then this one operates at high temperature. And in that case, helium is the favored coolant. If you build such a reactor, you'll find that you have a core average power density of 7 megawatt thermal per cubic meter. However, most of the reactors in existence today use light water, and we'll differentiate later between light water and heavy water. And most of those reactors operate using pressurized water. So we pressurize the water so that we don't allow it to boil. If you pressurize water in your car, you'll find that the steam there pressurizes a little bit, and the water is not boiling in cooling the car. However, another design allowed the water to boil, so we designate it as a boiling water reactor using H2O. Here we are differentiating between H2O and later on D2O that is used in another type of reactor that has been developed by Canada. Heavy water uses D2O, where deuterium replaces the hydrogen. Now, when you pressurize the water, in this type of reactor we designate as a pressurized water reactor, you can have a much higher, 10 times higher core power density compared with the high temperature gas cooled reactor from 7 to 75 megawatt per cubic meter. The boiling water reactor, you allow the water to boil there in the core, decreases that value to 50 megawatt thermal per cubic meter. And we can design even system now that is like the liquid metal fast breather. In a liquid metal, instead of using water or helium as coolants to reject the heat in the flow system that we have to establish in that type of a design, and all designs, in fact, you use liquid metals. And one of them, a choice one, is sodium. Sodium at room temperature is a metal, of course, that is a solid, but when you heat it, it becomes a liquid. Sodium is not as good as hydrogen in or graphite, carbon in thermalizing the neutrons. So the neutrons remain fast, and when they are fast, it allows us to better apply the equation that I gave you in an assignment, where you can breed plutonium from the uranium-238, or uranium-233 in the last assignment from thorium-232, because the neutrons are not thermalized in the case of the sodium. Sodium does not get the neutrons to lose their energy or thermalize them as efficiency as hydrogen in water. You'll find that you can breed. In that case, you also can operate at much higher temperatures. And because you operate at much higher temperatures, you'll find that the core power density is much higher. You produce more energy per unit volume. Look at this. This is about 10 times let's say here, even 10 times the power density in a boiling water reactor. What is the implication of why should we go, or would we like to go to high power densities? Because in that case, the volume of the core would be much smaller for the same amount of energy that we produce. So this one is about 6 cubic meter for a liquid metal fast breather, but it's 40 cubic meter for a pressurized water reactor. The energy here, if you want to compare it, 1 megawatt thermal per cubic meter is the same as 1 watt per centimeter cube. So consider that 75 here is the same as a 75 watt bulb producing energy in 1 centimeter cube between, say, your fingers. So it is not a very high really energy production. The temperatures that we use there are in the range of 350 degrees Celsius. Here, the temperature is much higher and much more efficient. However, when we go to higher power densities, then you are producing more energy per unit volume in a smaller volume. Well, economically, it means that the cost would be lower because you have less material, the smaller volume, but at the expense of a decrease in safety, because then you are producing more energy in a smaller volume, and you have to implement more stringent safety considerations. So here is a list of different types of power plants. I expect you to try to remember what are those acronyms. PWR is pressurized water reactor, BWR boiling water reactor, HGR high temperature gas cooled reactor, LMFBR liquid metal fast breather reactor. I added here to the list advanced gas cooled reactor that was developed in the UK some period ago. It used CO2, carbon dioxide, as a gaseous coolant. The high temperature gas cooled reactor also is a gaseous reactor. It uses helium. The liquid metal fast breather uses sodium. And there is another design called the gas cooled fast breather reactor. It is gas cooled, but you don't use graphite as a moderator. And in that case, also helium is used. Let's look at the temperatures that these different systems use. You'll find that the pressurized water reactor uses a temperature, exit temperature of 330 degrees Celsius, operating at 158 atmospheres. So that's a high pressure here of the pressurized water reactor. Boiling water reactors, because we allow the water to boil inside the core, you notice that it operates at a lower pressure of 71 atmospheres. The liquid metal fast breather, as you could very obviously operate at a much higher temperature, 615 degrees Celsius. So we expect that system here to operate at higher efficiency. And in fact, it also uses lower pressure. So instead of 158 atmosphere, it operates at a lower atmosphere of 10 atmosphere only. So because of the different design temperatures and operational parameters, you'll find that those systems have different efficiencies. The PWR, the pressurized water reactor, and the boiling water reactor, these are the two systems that we study in more detail, but these are primarily the systems used in the production of electricity from nuclear fission in the world today. They have an efficiency of 33%. So that means that 2/3 of the energy available to us is sacrificed in establishing that flow system. The cycle efficiency is rather low. Because with the advanced gas-cooled reactors, we operate at higher temperature, 640 rather than 330, you'll find that the efficiency can be increased to the 40%, 38%, 42%, and 36% for the liquid metal fast breed at 42%. The coal-powered power plants, power plants have an efficiency in the range of the 40%, like the liquid metal fast breeder reactor in general. What kind of fuels do we use? You'll find that primarily in the existing systems, we try to reach the highest possible temperature by using a ceramic. And the ceramic, like chalk, in fact, you can consider it as a ceramic. In the case of the PWR and the BWR, we use uranium dioxide, and the high temperature gas cooled reactor now uses some designs use uranium dioxide, but to get to higher temperatures, we use, say, uranium carbide. The liquid fast breeder uses a mixed oxide of uranium dioxide and plutonium dioxide. When you use the carbide, you can reach obviously higher temperatures. If you want to use light water, we are using H2O, you'll find that the hydrogen there absorbs many neutrons. So the natural uranium comes in with a content of uranium of 0.72%. You cannot choose natural uranium with a pressurized water reactor or a boiling water reactor. We have to increase the concentration of uranium-235 to 3.1% or 3% for either one of those systems. You find that for the liquid metal fast breeder, we have to increase that composition of uranium to the 12% or even the 20%. For naval reactors, even if you use a pressurized water reactor, you have to increase that enrichment or uranium to the 96% uranium-235 rather than the 0.72%. And this is going to be a process of what you call enrichment that has to be used to be able to use to our advantage the existing uranium in the Earth's crust. In that case, we also convert some of that uranium-238 into plutonium-239 that we can use in a liquid metal fast breeder. And the amount of fissile material that you produce relative to the amount that you burn can be 0.6, meaning that you create on the average 0.6 atoms of, say, the plutonium-239, which is fissile relative to the number that you burn. If you go to the liquid metal fast breeder and say use what's called the mixed oxide here of uranium dioxide and plutonium dioxide, that conversion is now designated as breeding ratio. Look at this, it's larger than 1. In the gas-cooled fast breeder reactor, it's also larger than 1. What does it mean? It means that we are producing here 27% more fuel than the fuel that we are burning. Here we are producing 39% more fuel than the fuel that we are burning. And this is the only process in nature where, as you are producing energy, you can create even more energy. And that is part of the vision of nuclear energy. If humanity, or as a technological civilization, adopts it, basically you have here an unlimited supply of energy. As you are producing energy, you are even producing more energy if you would like to do it. In existing systems, that is not the case. We are really using a wasteful system in which we are really depleting our resources of uranium-235 here, and here. Sometime in the future, the high-temperature gas-cooled reactor would allow us to exploit the thorium cycle. And in the thorium cycle, like in the last assignment, when you absorb a neutron, you turn it into thorium-233. It emits a neutron, it turns into protactinium-233, and then that protactinium itself turns into uranium-233. So, and thorium is 4 times more abundant in the Earth's crust. So in a way, we can also generate breeding of more fuel than we consume. Let's remember this, that this is the promise of nuclear energy, of its vision. If we adopt this design of the liquid metal fast breeder, which is not the case today, we're still using the light water reactors, PWR and BWR, then we can produce more energy than the energy we are producing. If we are going to use nuclear energy, we know that the fission process produces fission products. Those fission products are very highly radioactive. So even though in fossil fuel productions, when you burn petroleum or you burn coal, the products of the combustion gases are so huge in size that we cannot contain them. So what do we do with them? Oh, well, we dilute them. We release them to the environment and pollute our environment. In fact, it's like fish in a fish tank destroying their own environment. And we are releasing, as we all know, the carbon dioxide, causing some forms of climatic change. We are also releasing the nitrogen oxides. We are releasing the sulfur oxides, SO and SO2 and NO and NO2. Both of them absorb water from the atmosphere, turned into sulfuric acid and nitric acid, and then we inhale those two into our lungs and get sick. We also turn our lakes and our oceans into becoming more acidic, threatening life in those two components of the Earth. So we are using in fossil fuel production open systems for the disposal of the product of combustion. And in addition, we add, when we burn coal, we release the particulate matter to the atmosphere, and some of it contains radioactivity from uranium. In contrast, for nuclear energy production, the amount of waste are very small. A typical 1,000 megawatt power plant can produce maybe waste the size of a desk, 1 cubic meter of high-level waste every year. So we have the luxury here of being able to contain it. So nuclear power systems, fission systems, are closed systems. The product of combustion, the fission products from the fissioning of uranium, are contained. And in the same way that we mine the uranium out of the ground, we simply can take the waste and bury it back into the ground. Nevertheless, in power operation, we want to maintain the system as a closed system. So we use multiple barriers to prevent any release of radioactivity under normal operation. It doesn't mean that in the case of accident, some of those products are released to the environment, and we'll study that later on. So the first barrier or layer against the release of the fission products is that we use ceramic fuel pellets. Uranium dioxide is a ceramic. First, it can take high temperature, that's true, but it's also porous. And some of the fission products are gaseous, like at room temperature, they're liquid like iodine, but at a high temperature of operation, they are gaseous. Xenon and krypton are also gases. generated from the fission process. So they are contained within the pores of the ceramic fuel pellets, and that is our first barrier about releasing radioactivity to the environment. Those pellets are contained inside a metallic can or a cladding, and I'll show you a picture of it as we go along. That would contain the fission products, gases and solid. Those metal elements, the fuel elements, are contained inside the reactor vessel and the piping that also doesn't allow it to be released to the environment. Those pressure vessels for the pressurized water reactor can reach 8 to 10 inch of plates that are cast and then even welded together using explosive welding. The reactor vessel is surrounded by a concrete shield to protect the personnel in the plant against the gamma radiation. And the whole thing is contained within a containment structure that we'll describe in more detail. Power plants are built in an exclusion area where the population density is controlled. So in the case of an accident, they are not affected by the any release of radiation. And there is a plant separation distances from the population center when we site nuclear power plant. So you'll find that different power plants have what we call the ESFs, or engineered safety feature. And we adopt the defense in-depth design principle in that we, under normal circumstances, no radioactivity is released to the environment. However, accidents can occur if those ESFs or engineered safety features are not functioning according to their design. And that can be caused by equipment failures, human error, or severe natural events. Like we take Fukushima, that was a severe natural event, an earthquake caused a tsunami that flooded the equipment of the plant. Human error, that was primarily the case of Chernobyl. People who ran the plant did not know how to run it. They didn't follow the safety procedures. Equipment failure is what happened primarily in the 3 Mile Island, and the combination thereof of the 3 causes: equipment failures, human error, and natural events. So when we design nuclear power plants, we have to take these into account in what we call the engineered safety features. So let us list here the engineered safety features that are existing in the pressurized water reactor. So you'll have a core where the fission process occurs. The first engineered safety feature is the control rods. If those control rods are inserted into the core, you are shutting down the chain reaction. There is also a system that injects boron into the coolant. Boron is a very strong absorber for neutrons. So in case you cannot insert those control rods, material that absorbs neutrons, to shut down the chain reaction, you can inject the boron as a liquid and as boric acid. And in that case, it's enough to shut down the plant. So here we have 2 engineered safety features: the control rods and the boron injection system. If any earthquakes occurs and breaks one of the pipes, steam would be released in the containment structure. So you have a containment spray that would quench the steam. And in that case, it gets water from an engineered safety feature called the refueling water storage tank that would spray the containment structure. The water there would condense any steam or quench it. It goes to a containment sump water that is taken to a heat exchanger called the residual heat removal system. And something interesting about nuclear power plants that differs them from existing, say, fossil fuel power plants or coal power plants is that even if you shut down the chain reaction in the core, you would reduce the power from 3,000 megawatt thermal generated to still a residual power, or what we call the residual heat or the decay heat from the radioactivity of the fission products, still emitting beta particles, electrons, and gamma radiation. You find yourself with an 8 megawatt out of 3,000 megawatt still being generated for about a 24-hour period. So now you have to cool that residual heat with an external HX, stands for heat exchanger. So residual heat exchanger is another safety feature that allows us to extract the heat after the chain reaction is stopped for a period of 24 to 48 hours. However, if you're not able to extract that heat, you could still melt the core and cause a release of radioactivity. That happened in the case of the 3 Mile Island. They were not able to extract that decay heat for enough time for it to come down to a safe level. The same happened in the Chernobyl as well as in the Fukushima accident. So dealing with that decay heat system is an important design aspect that your generation of engineers should deal with. It is possible to deal with that problem if you continuously extract the fission products from the core. Then that problem would be totally eliminated. We can talk about these interesting design features for future designs later on in the semester. If an earthquake happens, that would prevent your core from being cooled. And if you don't cool the core, extract the energy release from the fission process or from the decay heat process, your core will melt. So the loss of coolant associated with an earthquake would mean that the pressure in the system would be decreased. And the sensors will sense that, and immediately, if the pressure decreases below 20 atmospheres, we have what is called the accumulator tanks. With under nitrogen pressure, the water is automatically injected into the system to cool it. Now, because the system is pressurized at a high pressure, about 2,000 pounds per square inch, if you try to inject coolant into it, you have to inject coolant at a high pressure. So in that case, you have a pump system that would inject water from the refueling water storage tank or from the accumulator tanks at high pressure. We call it the high pressure injection system. As an operator, you release the pressure from the system through pressurizers. The pressurizer component is not shown here. I'll show it to you later. If you decrease the pressure, then you can use that a low pressure coolant injection system, which is associated with a residual heat removal system. And in that case, because you are in a pump, if you pump at low pressure, you can have a much higher flow rate or throughput from the pump. So we have also a low pressure injection system into the core. So here we can list really the engineer safety features for the pressurized water reactor concept: the control rods, the containment vessel and its spray system, the accumulator tanks, the residual heat removal exchanger, the HIPSI or the high pressure coolant injection system. This is what operators name it, the LIPSI, the low pressure coolant injection system, the boron injection tank, and an excess supply of water in the water refueling tank. Wow. All right. So all of these are there to in the pressurized water reactor system. We go to the boiling water reactor system, and you have the same, some of the same components. The control rods, but instead of coming from the top, they come in from the bottom because you have lots of steam drying equipment near the top of the core. You still have the same containment spray. The boron injection also is the same, except that it used to be controlled by the operator in older BWRs. Now it has been turned into an automatic system to shut down the chain reaction. What is typical of the boiling water reactor is two components that do not exist in the pressurized water reactor. You have what's called the core spray system that gets water from a supply of water in an annular region here in the same of a toroid called the pressure suppression pool. You spray the core. If you spray the core in the case of a loss of coolant, again, the worry is an earthquake breaking the coolant line from the main feed water from the turbine plant. And in that case, You spray the core to cool it and prevent it from melting. You have a low pressure injection system, a high pressure injection system. You have a residual heat removal system. And instead of the refueling water storage tank and the accumulator tanks, we have a condensate storage tank as an extra supply of water and water in that pressure suppression pool. The idea here is that if steam is released in that containment structure here, it is bubbled into water to condense it. In addition, you have the containment spray itself, and that also goes back to through a sump to the water suppression pool. So if we want to list the engineered safety features of the boiling water reactor, they have the control rods, the containment spray system, the pressure suppression pool is typical of the BWR, a residual heat removal system, a high pressure coolant injection system, a low pressure injection system, a boron injection tank, and the condensate storage tank instead of the refueling water storage tank in the PWR, and an internal core spray system. So all of these are systems that prevent the release of radioactivity in the case of an accident. Now the question is, what thermodynamic cycle is used? In existing PWRs and BWRs, because we are producing steam, what is used is what's called, of course, in thermodynamics, a steam turbine cycle, or also named the Rankine cycle. And so what do? You from feed water heaters, you send your water into an economizer, then an evaporator, you turn into steam, you can superheat it, then take it to a turbine, expand it, and then reheat it, and expand it again, and then reject the heat to the environment to create the flow system. Operational temperatures in Fahrenheit are not very high. They are in the range of 500 to 1000, the best that you can get with the steam turbine cycle. So the attention of the designers and for new designs of nuclear reactors is to improve the efficiency. Hence, we need to operate at higher temperature. So under consideration is the Brayton cycle, also called the gas turbine cycle. As you'll see, you'll have now your turbine, your steam turbine along the same shaft as the electrical generator, and you can reach much higher temperature, as you can see here, 1500 degrees Fahrenheit. So you add the heat to the working fluid, the gas in that case, it's a gas turbine, either CO2 or helium, and then expand it in a turbine. You extract some of the heat of it, it's called a recuperator. That heat is taken from here and you add it to the coolant before you add it back into the reactor. So you try to enhance the efficiency by not rejecting all the heat to the environment. But then after the coolant goes through the heat rejection process, you take it to the compressor where it is compressed, and the cycle goes on. Now, after compressed, you add the heat from the recuperator to the heat addition in the core of the reactor, and then expand. Definitely, the gas turbine cycle promises us efficiencies in the range of 40%, whereas the light water reactor steam turbine cycle is limited maybe to the 30% efficiency. So the emphasis of engineering for new designs is really the gas turbine cycle. All right, so let us study those cycles in more detail and also think about other cycles that we should consider in the future. The main cycle today, as I suggested, is the Rankine or the steam turbine cycle. On the drawing boards for future systems, we are talking about the Brayton or gas turbine cycle. The French like to call it the Joule cycle. All right, so now we know that this uses a gas turbine and can get us higher efficiency. Gases that are candidate is CO2 or helium, and you can also use steam, in fact, or you can use hydrogen, but it is explosive. Some suggestions have been made about another cycle, especially used in space applications, and that is what's called the Stirling cycle. The Stirling cycle is an external heat engine cycle. So that's in contrast to the internal combustion engine or the ICE cycle. In the Stirling cycle, the cylinder that is moved to produce a mechanical power into an electrical generator is heated from the outside. Hence, it is ideal for thermal solar. When you concentrate solar energy on the external cylinder, then the Stirling cycle would be the best cycle to use in that case. In the space applications, you could use a radioactive isotope, or you can use some fission products. In fact, used fuel to heat the working cylinder from the outside. So the Stirling cycle is suggested for applications, specialized application, and it has a fascinating possibility here in that it can attain the ideal cycle efficiency of the Carnot cycle efficiency. Other interesting cycles that have been studied, I had one of that is a dissociating gases cycle. And I'll show you the promise of it. It was used by one of my students for an engine for a naval reactor. And in that case, I'll show you the advantage. It has also advantage in space applications. I'll describe to you why is that so. In the dissociating gas turbine cycle, you heat up a working fluid like nitrogen tetroxide, N2O4 chemical. And when you heat it to high temperature, you dissociate the gas into from N2O4 into 2 molecules of NO2. And when you cool that NO2, the process reverses itself back to N2O4. Now, this is a gas, and the energy that's produced from a gas is is according to the ideal gas equation. The work done would be P, the pressure, V, the specific volume. And in that case, instead of nRT, you have twice nRT. So you have double the number of molecules that do work in the gas. If you double the number of molecules, you double the heat transfer process, and you can lower the volume of your heat transfer equipment very significantly, as I'll show you in a moment. There are many candidate dissociating gases. So we showed you the nitrogen tetroxide turning into 2 NO2. In that case, you turned the initial molecule into 2 molecules. That can happen with aluminum bromide, aluminum chromide, chloride, and aluminum iodide. There are cycles that even can have an increase in the gas factor, not just 2 here, but up to 6. Look at this. If you use aluminum chloride plus aluminum as a liquid, you turn it into aluminum chloride with a gas content of 6. Wow. You increase the number of molecules carrying, doing the work by a factor of 6. They operate at different temperature ranges. N2O4 operates at a very low temperature, 170 degrees Celsius. But if you go to the aluminum bromide, you reach 300 to 1400 degrees Celsius. So now that you have doubled, or you can even go to 6 times the gas constant, what advantage do you get? So let's compare 2 steam turbines. A steam turbine using water, like a conventional steam turbine cycle, for a power plant, a fission power plant of 500 megawatt electric, meaning that it's about 1500 megawatt thermal. We can compare this to an aluminum chloride gas turbine. This uses steam, this uses a gas. The gas is aluminum chloride, producing 555 megawatts. So it's a good comparison between the design. The pressure is much lower in the case of the aluminum chloride. That's an advantage in the design. Here the pressure is 240 atmosphere, absolute. And let's just go to the end of the design feature here. you'll find that in the case of the steam turbine, the turbine length would be about 30 meters. If you take the aluminum chloride, because now you have more molecules doing the work, that 30 meters becomes only 9 meters, 1/3 the length. If you have a much shorter turbine to produce the same amount of power, the weight of the turbine is decreased from 964 tons, metric tons. 1 metric ton, remember, is 1,000 kilograms, from 964 tons into just 55 tons. The comparison here is the power to weight ratio. So if we take the megawatts, 500 megawatt of power that you can produce, divided into the weight of the engine, 964, you are producing 0.5 megawatt electric per metric ton of the machinery that is producing your electrical power. That factor is 10 in the case of the aluminum chloride. So if you take 10 here, divided into 0.5, that's 20. So you'll find that in terms of the figure of merit, the power to weight ratio of the dissociating gas, it's 20 times what you would get in a gas turbine. So in that case, if you want a small volume and a small weight of the turbo machinery, definitely you go to a dissociating gas. It's a factor of 20 advantage. And so if you want a nuclear submarine that would have a low weight, large power to weight ratio, definitely dissociating gas would be a good choice. If you want to launch turbo machinery into space or in space applications in general, definitely using a dissociating gas rather than a conventional system would give you a factor of 20 advantage. And notice also that it will cost you less to put material heat transfer equipment into space. So and you can use it on Earth. So why isn't it used all over the place, since we have that huge advantage? It's that because the aluminum chloride or the nitrogen tetroxide are toxic substances. They're not the same as water in general. All right, so that's a disadvantage. But we use toxic substances in many applications, like gasoline is a toxic substance from all perspectives. Another interesting cycle that can be used in nuclear power plants. I had a student applied to a boiling water reactor using an exo type of analysis. Here is a Kalina cycle. So what is a Kalina cycle? Kalina is the name of a Russian scientist who came to the United States, to Florida, and applied his idea of a cycle to geothermal energy. We talked today about geothermal energy. It is a cycle that uses, you can call it dual coolant cycle, a mixture of 70% NH3 or ammonia and 30% water. And when you use this type of a cycle, you know that ammonia, you use it for windshield wiper fluids and for cleaning up mirrors, say in the bathroom, that ammonia is used as a cleaning material. So it's a very common material, NH3. But again, it is some kind of toxic too. You don't want to inhale it into your lungs. But ammonia, as we all know, has a very low boiling point. So in that case, it can be used in thermodynamic cycles that have a low temperature working fluids, and geothermal heat has a low temperature. Now, what if we apply to a nuclear reactor? A student working with me for a boiling water reactor applied it to a boiling water reactor and discovered that it can enhance the efficiency by a factor of 30%. So these are cycles that are worthy of development and investigation for the future. Let's quantify the processes that I can give you some interesting problems to work on. We define the heat input to a thermodynamic cycle dQ as T delta S. So we define the entropy as dQ divided into T. Now here, when you use any thermodynamic equations like the Carnot cycle efficiency, remember that you use the Kelvin degrees, 273 plus degrees Celsius. You do not use the Celsius or Fahrenheit degrees in general. You can also use the, if you use the British, if you use a SI system, that's 273 plus degrees Celsius. If you use the British system, it's degrees Rankine now. That's 460 plus degrees Fahrenheit. And here we do not use the designation degrees Kelvin. We just call it the Kelvin. Anyway, in any case, if you integrate for dq, you'll find that if you integrate the temperature, the Kelvin temperature over the entropy ds, you can get the heat generated. And in design applications, we use what's called the Moliere chart that shows the entropy against a quantity that we call the enthalpy, which is really nothing but the total energy in the system. You'll find that Moliere, first you can use a TS diagram, the T temp, T kelvins against entropy. You could see the graph here. You'll find this as a chart in the back of any thermodynamics book. It shows, I'll show later what is shown on it. And the Moliere chart is shows us the enthalpy that's used more than the TS diagram against entropy. You could see here that this is a region here for any working fluid that shows the quantity of the enthalpy. Let's define the enthalpy. You know it already. It's a flow energy, which is PV plus the internal energy. So it's PV turned into unit of kilojoule per kilogram plus the internal energy. That is what we call the enthalpy. So that enthalpy of a working fluid is plotted against the entropy. So that's H against entropy. The unit of enthalpy is kilojoule per kilogram. You'll find that it goes up here, reaches a maximum point, and then comes down. And this is subdivided into ranges, 0.8, 0.98. This is the quality of the steam in that case. This is called the saturation line, where here at that point, say it's 0.94 steam to and 0.06 liquid. When you add the heat from the left side to the right side here, you turn your water into steam. And when it is 100% steam, the quality factor is 1, and that's what we call the saturation line. But then those lines here extend as constant temperature lines or isothermals. So that's a steam at 200 degrees Celsius, and a pressure shown here of in Pascal or atmospheres. You see that as you increase the temperature, you go up in the diagram. Every point above what's called the critical point here is now a gas. So it's a steam, and this is called the critical point. In the design of thermal systems, we like to use this Carnot cycle efficiency, which is defined as the network output divided by the heat input. As a reminder, you have seen that before. That's a heat addition minus the heat rejection divided by the heat addition. And that describes for us the pressurized water reactor. You find that you add the heat QA here in the reactor core. We turn it into steam, we take it to a turbine, we expand it in the turbine. Then we use a condenser to turn the exhaust from the turbine into a liquid again, and then we return it back to the reactor core. Along the turbine shaft, we have an electrical generator that produces for us our electricity. We can show that process on the TS diagram as adding heat at point 1 from point 1 to 2 at constant temperature. So that's isothermal temperature T1, expanding the turbine from 2 to 3. If you go back to that same diagram here, that's expanding it from 2 here, 0.2 to 0.3, and then rejecting the heat to create that flow system. So you could see here that you have a high temperature reservoir to a low temperature reservoir. You reject the heat from 3 to 4, and then from 4 to 1 you return the liquid back to the heating part, which is the reactor itself. From 4 to 1, you are practically pumping the water here from the condenser well to the inlet to the core of the reactor. If you apply the Carnot cycle efficiency equation, you'll find that it ends up with an efficiency. The heat that you add is T delta S. The heat you reject is T rejection delta S divided into the heat addition. Delta S, delta S, delta S cancel. In the case of an ideal system where you don't have any inefficiencies, and in that case, it's the heat addition minus the heat rejection divided into the heat addition. Sometimes it's written as 1 minus T sub rejection divided into TA. Please remember, because some people still make that mistake, when you substitute for temperature in the Carnot cycle efficiency, it's Kelvins, not Celsius, not Fahrenheit. And I'll give you a problem so that you can remember this for the rest of your career. Some people still make the mistake of substituting the wrong units in general. Example of the Carnot cycle efficiency applies directly to the case of the boiling water reactor. In the case of the pressurized water reactors, we do not produce steam in the reactor core itself. We take the pressurized water there. We don't allow it to boil because the PWR system was invented primarily for nuclear submarines. You don't want to produce steam in a water that would be sloshed around by the waves in the ocean. So you take the pressurized liquid in the pressurized water reactor and take it to heat exchanger, exchange there the heat into turn it into steam, and that's a steam that goes to the turbine. So you have here in that case some forms of unavailability between the temperature at which you are causing vaporization and the temperature at which you are reducing condensation. So we define the efficiency in a slightly different way as the work done in the turbine minus the work done in the pump divided into the heat addition. And we can express that in terms of the enthalpies rather than just the temperature. So the work done in the turbine would be the enthalpy at 0.1 minus the enthalpy at 0.2. The heat of addition would be from B to A here when you pump the water in the feed water heating and then add it into the core of the reactor in the heat exchanger in case to cause vaporization. And that's the enthalpy in the from H, the work in the pump is H sub B minus H1 in the diagram divided into the heat addition from point 1 to point B. That point 1 and point B where you pump the water adds some heat to the working fluid, but it's a very small. So if we take H sub 3, the enthalpy at 3 equal to the enthalpy at B, you find that, oh, well, they're very close to each other, and you get a very simple expression for the enthalpy of the pressurized water reactor. The enthalpy at 1 at the turbine minus the enthalpy at 2 when you expand in the turbine divided into the enthalpy H1 minus H3. That's where the heat added to the system. So you use this on the Moliere chart now as an example here. You choose a working point where you have operating at a given pressure of the reactor. At a given temperature, the 2 points interact at the point here B, and this would be superheated steam. If it were on this line, it would be saturated steam. You expand it to a point P sub 2 to a given pressure line or a given isothermal, and you get the 0.1 enthalpy, the 0.2 enthalpy, and you can substitute in that equation to get the efficiency in general. There are ways of maximizing the efficiencies of those cycles, and we'll leave this for next time since we reach the limit of our lecture for today. I'll be available for any questions. Remember that, let me see if there are any questions in the chat room. I'll be, will the exam, when and where will be the exam this Friday? This exam will be for 24 hours for you to solve a take-home exam that would be available on the web page where you find the assignments. Okay, Simon Zhang, did I answer your question? You have 24 hours to solve the problems. Up until what topics will be covered on the exam? Until the topic for the class before Friday. So today's topics, of course, will be included. The topics on Wednesday. I used to have the topics on Friday also covered, but we are not going to have a class on Friday to give you time to revise the material. No, and then send it to me. Do we submit it on Canvas? No, you submit it to me personally on my website, and I'll give you, you remind me now, I'll give you where to submit it, because the assignments are being graded by our wonderful TAs, but I grade the exams myself so that I can tell really what has been learned and what has not been learned. So we don't submit it on Canvas, you submit it back. I'll make sure that I specify that. But we still have the lecture on Wednesday that would be included in the exam. And we have covered enough material for you to revise it and review it before I can give you an exam on it. What will be the format of the exam? Multiple choice, calculation, short answer, etc. The engineering tradition is that to give you problems to solve. So the format answering Sirman Vinayak is the same as the assignments. Problems that you have to solve, definitely somehow similar to the assignment, but not exactly the ones in the assignments. What will be the format of the multiple choice? Okay, perfect, thank you. You shouldn't panic, but if you would have worked on the assignments and you understand, you read the lectures, you came to the lectures too, you're almost ready for an A+. Okay, any other questions, any that I can answer? I'll be available if necessary the whole afternoon answering questions. And remember that we have two wonderful TAs, Anchal and Alvaro, that you can ask questions. Their office hours and contact email are available both on the web page as well as on the Canvas. I gave it to you in two places. All right, have a nice afternoon, everybody. If you have no other questions, but I'll be available for answering questions. The recording should have